What if you could measure electrical current without touching a single wire? In this video, I'll show you the working principle of Hall effect sensors and how it make that possible. We'll explore how the signal flows and look at a real example in action. Let's dive in. Hall effect sensors are typically made from a thin, rectangular piece of P-type semiconductor material, such as gallium arsenide, AAS, indium antimonide, INSB, or indium arsenide, INAS. A continuous electric current is passed through this material. The charge carriers moves in a straight line from the negative to positive pole. When the device is exposed to a magnetic field, the moving charge carriers, electrons and holes inside the semiconductor experience a Lorentz force. This force causes the charge carriers to be deflected toward opposite sides of the semiconductor slab, pushes the carriers sideways. As a result, electrons accumulate on one side and holes on the other. Note, electrons is the negative charge carriers, holes is the positive charge carriers, or simply absence of electrons. As a result, a voltage difference appears across the material, perpendicular to both the current and the magnetic field. This voltage is called the Hall voltage, and it is directly proportional to the strength of the magnetic field. The output voltage of a Hall effect sensor is often very small, sometimes just a few microvolts, even under strong magnetic fields. To enhance performance, most commercial Hall sensors include built-in DC high-gain amplifiers. Depending on how the Hall effect sensor is designed and what it's used for, its output can be either analog or digital. Analog Hall sensors generally include voltage regulator to maintain a stable supply voltage to ensure consistent sensor performance, a Hall element, the core sensing component, signal amplifier to boost the small Hall voltage, often in microvolts, to a usable analog output level, millivolts or volts. The output of an analog Hall effect sensor is a continuous voltage signal that is directly proportional to the strength of the magnetic field it detects. One common application of this type of sensor is in current measurement, for example, a clamp meter. Digital Hall effect sensor typically consists of voltage regulator, Hall element, amplifier, comparator or Schmitt trigger to convert the amplified analog signal into a clean digital signal, on-off, with hysteresis to prevent false switching due to noise or minor magnetic variations. Output driver to send the final digital signal, high or low, to external devices such as microcontrollers, relays, or logic circuits. Digital Hall effect sensors are used in many applications where a simple on-off binary magnetic detection is needed, like proximity detection. Before we finish, let's see a live demonstration of how an analog Hall effect sensor is used inside a clamp meter to accurately measure current without direct contact. To measure both alternating and direct currents, Hall effect clamp meters use firm iron jaws that help concentrate the magnetic field around the wire. When the jaws are clamped around a conductor, the magnetic field generated by the current is directed across a small air gap in the core. This gap is located where the tips of the jaws meet. The presence of this air gap helps limit the magnetic flux, preventing the core from saturating under high current, a condition where the core becomes overloaded and can no longer accurately respond to increases in current. Without this air gap, strong magnetic fields at high currents could saturate the core, causing the sensor to lose linearity and give inaccurate readings. You can usually spot this gap as a narrow space between the jaws, often covered by a thin layer of plastic. Inside that gap is the Hall effect sensor, a small semiconductor device that directly measures the strength of the magnetic field. As current flows through the wire, the magnetic field passes through the sensor, generating a small voltage. This voltage is then amplified and scaled to represent the true current in the conductor. After the Hall effect sensor detects the magnetic field around the conductor, it outputs a small analog voltage proportional to the current. This signal is then amplified and filtered by an operational amplifier to make it readable. Next, it goes into an analog-to-digital converter ADC, which converts it into a digital value. The microcontroller processes this data, applies scaling and calibration, and then sends the result to the display to show the actual current in amperes. Thanks for watching. I hope this video helped you better understand how Hall effect sensors work and how their signals are processed. If you enjoyed it or learned something new, feel free to check out more content, and I'll see you in the next one.